to be looking at section 6.2. Does anybody have any homework questions? This is a picture from 6.2. The material in 6.2 is used to show how many platonic solids there are. So we have here an example of a platonic solid, the dodecahedron, and it turns out that the poliovirus shell is a dodecahedron.
Did you say like these questions on the section 6.2?
We're going to be doing 6.2 next today.
Oh, I thought you were.
Okay. And I have a note to remind me to tell you to bring scissors, tape, and 2 markers to class on Wednesday. Okay, so Wednesday you need 2 markers. I'll be using blue and red, and some scissors and tape. This section 6.2 opens with a question, can I read your psyche? So here's what we're going to do. I don't think I'd want to read your psyche. I mean but here's what we're going to do in 6.2. Now, see how I'm looking at you and not my paper? I'm going to make a squiggly drawing without looking at the paper. And then in a minute, I want you to make your own squiggly drawing. Don't try and copy mine. Don't make it too complicated or it'll be too hard to count. So we're going to make a squiggly drawing there. I'll just look at it enough to fix the part I just did my pen from. Okay. So go ahead and make your own squiggly drawing.
I already did.
You already did yours? Okay. And we're going to count parts on that squiggly drawing. But before we do that, the author asks if I can see your psyche, and the first thing is that wherever you have lines crossing, we'll draw a dot wherever you have lines crossing. And 4 lines come out of those dots wherever you have those lines crossing. 4 branches come out of your dots. And you're like, well, that's pretty lame. Anybody can do that. I mean, there are lines crossing. Of course, there's 4 lines. Okay, so we'll try and get a little better. Also put a dot at the beginning and the end of your squiggly drawing. These are called vertices. So these points that we just drew in here are called vertices. I have 1, 2, 3, 4, 5, 6. So go ahead and count your vertices and write how many you have. Now we'll count edges. Now if you did like me and made little tiny places, then be careful when you're counting your edges. I'm going to follow through from the start to the end, and that's a good way not to miss any edges. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Mine has 9 edges. So count your edges and write down how many you have. And then faces are the enclosed areas and the outside. The outside counts as a face. I have a little tiny face right here. And right here, a little tiny face. So I have 1, 2, 3, 4, 5 faces. Okay, the outside counts as a face. Well, here's where we have something amazing. If you take your vertices minus edges plus faces, you will all get exactly what I got. 2. So this is why your author says, can I read your psyche? So you all have a different squiggly drawing, but you all managed to make vertices minus edges plus faces equal 2. Now sometimes, depending on your drawing, that's a little hard to see, so I'm going to come around and help you with that, and Nicholas can too, and we'll make sure that you can do this because this is one of the things that I would give you on a quiz. I'd say find how many vertices, edges, and faces this drawing has. Okay, so the beginning and the ending are vertices. So you put a little point there and then you have 5 faces. 1, 2, 3, 4, 5. The outside counts as a face. So this is 5.
6 vertices.
Well, because like these don't.
Oh, they're not touching?
Yeah.
Oh, okay, very good. 1, 2, 3, 4.
Yeah.
Okay, then they're on the floor. Okay, good, because then I was going to try and recount your edges. Because that wouldn't have worked then. Okay. How's yours?
I'm so sick. How do I do the edges and faces?
1, 2, 3, 4, 5.
So edges are the length of line in between each two dots, or like this. So follow from the beginning to end and count. Oops.
Is that enough paper?
How come you don't have? Oh, you took your pencil off the paper somewhere. Wait, is this connected right here?
It was.
Oh yeah, leave it connected. Okay.
I just thought.
Okay. Okay, now start at one end and go to the other.
1.
I think I have the same as her. Because I have 6 vertices, so it's 9 vertices.
Yeah.
Then
Five
you
edges.
should
But now do we
have
change
five.
vertices, right? Because
Yeah,
you took out two there.
Yeah.
Dude, I'm sad.
And then faces.
So those are the outside, and then the enclosed areas.
Okay, so it would be. This is an enclosed. Would it be the same?
So this is one, and this is one, and then the outside is one. So you have 3 faces.
Okay. I see. And then I do 4 minus 5 plus 2.
But you're already here.
Oh, you have a lot. You do. Okay, good.
I still can't go where it is.
Did you count the outside? The outside counts as a face. Okay, so that's probably what you're doing.
I think I have.
So start at one end and count, and then it's 6 in case you forgot. Okay, so start at one end and go to the other, and not up over two.
How do you do this?
1, 2, 3. Wait, how should I 5? Oh, 1, 2, 3, 4. What else?
Oh, wait, there's one here.
Oh,
That
that.
there.
Well, what about edges?
Now we gotta start over. So if you trace a line, then it's easier not to miss.
Will it be this to this? You get 9.
Every time we run into something,
So what does this equate
Yeah,
to?
is this the end?
It shows that every time we do it, we get 2.
Every single time.
Their ratio.
So that's the end. Three, 5, 6, 7, 8, 9, 10, 11.
Do you go on TikTok?
Like our senior year in high school.
It's just like right.
They like. So then when we went to study abroad.
There's like small stuff around,
I think
and they used this song, like one of the TikTok songs is like
at least by accident once, but it should be 1, 2, 3, 4, 5.
and it's like music. I like it.
And I had to.
Did you
go,
Why are some movies?
If anybody stopped,
That
raise
was
your
just
hand if
like,
you stopped.
the theater back then.
Did yours work out?
Yes. I copied yours to make sure I got it down and I got it.
Okay.
Well, what would you say?
So we are looking at Euler's characteristic of connected graphs. Euler's characteristic of connected graphs. It looks like it froze. Okay. V minus D plus F equals 2. So that would be something that you'd want to write on your quiz card, on your 3x5 card, because you'll use it for a question like this one. I'll give you a squiggly drawing to work on, and I'll also give you 2 of these quantities and ask you to find the third. And if you don't have Euler's characteristic of connected graphs written down, then you're going to have a hard time with that. Now, who is Euler? How many of you have heard of Euler before? Anybody? Yeah, you have? Good, good. So Euler is to mathematics what Shakespeare is to English, or what Michelangelo is to art. So here's a textbook by William Dunham, The Mathematical Universe. It's actually not a textbook, it's for reading, and it's very enjoyable to read. In it, I have some pages copied with Euler. He's my favorite mathematician. He worked in the 1700s right after calculus was discovered, and he just was amazingly brilliant. To put it in perspective, if I were to, I'm a lecturer instead of a professor because I did not pursue my PhD. I'm not interested in doing research, but Euler was interested in doing research. If I did go for my PhD, I would spend 3 to 5 years studying, coming up with a new theorem. Remember, we've looked at theorems. I'd have to prove it. I'd have to stand up to other people's attacks and make sure it was in fact correct. And it would take 3 to 5 years, and I'd have probably 20 pages written at the end. Not very thick to write a theorem. It's maybe even less than 20 pages.
Wait, how? That's what you have to do to become like
Yep.
accurate?
Yep.
To make a new theorem.
New theorem to be a professor in mathematics, yeah.
If you had to choose now, what do you think you would do?
No, I would not do that. I wanted to be a professor when I first came to the university, so I was planning to go back for my PhD, and then I saw I could choose teaching or research, and I saw what the professors here do, and I thought, you know what, I really like teaching. So, so I stuck with teaching. I do have a master's degree in math, so I have lots and lots of math, but not a paper. Well, Euler was amazing. I'll have to read what he did, because it's just so much I can't. Okay. He wrote, on an average, 800 pages of new mathematics per year over a career that spanned 6 decades. In the 1990s, they were printing his works, and they were over 300 pounds at that time, and they were not done. That's how prolific he was. His work was noted for its insight and beauty. Here's a little article from that book I was showing you. His work is probably the most influential textbook of modern times. It is the work which made the function concept basic in mathematics. It popularized the definition of logarithms as exponents and the definitions of the trigonometric functions as ratios. It crystallized the distinction between algebraic and transcendental functions and between elementary and higher functions. It developed the use of polar coordinates and of the parametric representation of curves. Many of our commonplace notations are derived from it. In a word, the Introductio did for elementary analysis what the Elements of Euclid did for geometry. Now he's doing all this while he's going blind with a painful eye disease. Yeah, and he still was a nice guy. The accounts of the day say he was a nice person. So this is one of the works that he did, Euclid's characteristic of connected graphs. And you might think, well, what does a squiggling drawing have to do with anything? It's part of an area of math called graph theory. So in your textbook in 6.1, we see another example of Euler's work. Here's the 7 bridges of Königsberg. So this is a city with 7 bridges on an island. And there was an open question at the time that Euler lived. The question was, can you go across all the bridges one time and come back to your favorite cafe? So start at your cafe, go across all the bridges just a single time, and get back to your cafe without covering any bridge twice. So here's how Euler described it. A problem was posed to me about an island in the city of Königsberg, surrounded by a river spanned by 7 bridges. And I was asked whether someone could traverse the separate bridges in a connected walk in such a way that each bridge is crossed only once. I was informed that hitherto no one had demonstrated the possibility of doing this or shown that it was impossible. Remember, that's one of the ways to prove something too, to prove that it's impossible. Well, Euler's brilliance led him to take these 7 bridges and distill them into their basic structure, which is points and lines. And that's why this becomes graph theory. Graph theory he distills into points and lines. We see this again in section 6.3, where we have water lines, electric lines, and gas lines going to houses. Or this is also done with railroad tracks. Or it was done using this idea of these lines and vertices. So we're just distilling these into their basic shapes, the points and the lines for graph theory. Professor Wenger, who was here many years, helped the Green Bay city decide where to put their next fire station. So they wanted to know where to put the fire station so that they could be close to nursing homes and schools, but not too far from the urban subdivisions. Where would that placement be best? And so graph theory is one of his tools that Professor Wenger was able to use to decide where the fire department's new firehouse should be stationed. Well, we're going to look at the Euler's characteristic of connected graphs for today. Oh, I was going to show you one of the most brilliant things that Euler did. It's just beautiful and elegant. He's the one who took our 5 most beautiful numbers in mathematics and connected them together. So he's the one who discovered that e raised to the I times pi plus 1 is equal to 0. So all the most beautiful numbers in math he brought together. Well, I know you want to know what kinds of quiz questions you can expect. So here's a couple of likely quiz questions. Given a connected graph, with 32 faces and 23 vertices, how many edges does it have? How many edges does it have? So we would use the v minus e plus f equals 2. We'd fill in the 23 vertices. We're trying to find edges, so I'll leave that. And faces, 32. Now as you're using the v minus e plus f is 2, you can go ahead and add the 23 and the 32 together. They're both positive, so you can add them up. So that would be 55. So you can add up the vertices and the faces together because they're both positive, and then you'll be having to subtract edges. Now you can do this in your head. You can think, what do I take away from 55 to get 2? Or you can, if you're more algebra inclined, you can go through the algebra, subtract the 55 from both sides. So negative e is negative 53. That means positive e is positive 53. So one type of quiz question is just answering what is the missing amount if you have vertices, edges, plus faces and 2 and is equal to 2 and you're missing one of those amounts. Another type of quiz question is your squiggly graph, so I will be giving you a squiggly graph for you to count the vertices, edges, and faces. Don't forget the outside counts as a face. If yours wasn't coming out, make sure you've seen myself or Nicholas to get that work done. Online students, feel free to email me your drawings. Let's try another one of those word problems. How about, given a connected graph, given a connected graph with 40 edges and 25 faces. Oh, thank you. Given a connected graph with 40 edges and 25 faces, how many vertices does it have? How many vertices does it have? V minus E plus F is 2. Okay, so this time we're trying to find vertices. There's 40 edges and 25 faces. So you can use your calculator to combine the negative 40 and the positive 25. So that would be leaving negative 15 on the left.
Is it under squiggly drawing?
Hmm?
We're trying to look at the canvas.
Oh, yep.
It says squiggly, okay.
Yep. So if you're looking at Canvas, this is what you would take a picture of. Put your name tag in it, which I forgot my name tag here. Where is it? Okay. Okay. Submit that to Canvas. So on this one we had edges and faces, which we added up, and then that left a negative 15, so we add positive 15 to both sides of the equation, and that gives us 17. Or again, this is the algebra approach. You can sit here and think, well, what do I take 15 from and get 2? Well, I take 15 from 17 to get 2. Does anybody want to try another one of these? Okay, we'll try another one. Given a connected graph, with 51 edges and 40 faces. Boy, aren't you glad you didn't have to count that many in your drawing? 51 edges and 40 faces. How many vertices does it have? So why don't you try this one, and I'll walk around and see how you're doing. And if you're stuck, raise your hand.
Yeah, I'm just starting this one again. Cause I did it, I like added 40 and 25. So I got like 65.
Oh.
But yeah, then it's, yeah.
So if you have a negative 40 and a positive 25, that would be a negative 15.
Right, yeah. Okay. Okay.
And that's why I have sausage.
I didn't symmetry.
Plus 40. 51 plus 40 is negative 11. Oops.
You have a easy calculator. You're probably following along with the negative 15 if you're following along.
No, I just didn't know. What did yours come out to?
Oh, I got 15 so.
Oh no, I got 16.
Is there anyone who didn't get a chance for us to look at? So the two numbers that you have in your v minus e plus f equals 2 equation, the two numbers that you have you can combine together. Okay, if one is negative, then make sure that it gets subtracted from the positive one. Anybody have any questions on using this formula? All right. Well, let's talk about why. So in the past we have looked at some proofs, but this time we're just going to consider why by going through what the proof shows. We're not going to go with a full-blown proof. The life lesson in this section is to start simple and build up, and that's what we're going to do here. Sometimes when you start simple and build up, the answer, the reason is very apparent, and you wonder why nobody noticed it before. So first, we'll start with the simplest connected graph. By the way, a connected graph just means that you can get from one part of the graph to the other without lifting your pencil up by tracing. So if I wanted to go from here to here on my connected graph, I could follow along the drawing without lifting my pencil up. Okay. We'll look at some graphs that are unconnected in a little bit so you can see the difference.
So they don't necessarily have to like cross, like it can be something as simple as that, like
Yes.
straight line.
It can be something as simple as a straight line, and they don't have to be curvy either. So start simple. We'll just put a straight line. Remember the outside counts as a face. So there's one face. So one face. The edges, just one edge, but two vertices. So vertices minus edges plus faces comes out to 2. Now we'll add an edge. So I'll take my simple drawing and add an edge to it. That added a vertice also. So now my vertices are 3, my edges are 2, and I still just have the outside face. So faces are enclosed regions. Okay, faces are completely enclosed, or the outside. So I still just have the outside face. Let's add another edge. Now you could just add your edge so that it didn't make a face, but let's add our edge so that it does make a face. So here's what we have, and now basically we have a triangle when I add another edge. So now we have 3 vertices, because I didn't add a vertice, but I did add an edge, and I added a face, because now I have an enclosed area, plus the outside counts as a face.
Why does the outside count as a face?
The outside counts as a face because later on when we do this in 3 dimensions, it will actually be a face. So we're going to look at this in 3 dimensions in a little while. That's a good question, though. Anybody have any questions so far? Once you can see why we keep getting 2, when you can see the reason why it comes out 2 even when we get more complicated, then speak up, and then we won't keep going anymore. Because we're trying to figure out why, and if you can figure out why, then we are done what we're supposed to. So we're at a triangle shape, and we're going to add another edge. Now you could add your edge out here, or you could add your edge here. There's a couple different ways you could add your edge. I'm going to have one going on the outside and one going on the inside and ending on one of the edges. So we're looking at why does vertices minus edges plus faces keep equaling 2? So this time we have 4 vertices, so that's one more than we had. We have 4 edges, so we added an edge, and we still just have the 2 faces, the inside and the outside. When I made this edge, I created another extra edge because I split one of the edges in 2. So I have 4 vertices, and now I have 1, 2, 3, 4, 5 edges, and I created a face. So I created a face and an edge. Okay, so these are 2 separate connected graphs. Anybody able to describe what's going on now as we add an edge?
Nothing changes.
Well, the numbers are getting bigger though.
Well, like that.
The outcome doesn't change. That's true. Why not? I mean, because these numbers are getting bigger. I add an edge, this number went up. Every time I added edge, the number went up for edges. In fact, here the number of edges went up to 2. Good. Yeah. So I'm adding edge, but I'm also adding a vertice. So when I add an edge, I have more to take away, but I'm adding in a vertice at the same time. Or if I'm not adding in a vertice, I'm adding in a face. Or if my edge is creating a new vertice and a new face, well then I've actually created 2 edges at that time. So every time we add an edge, we make the vertices go up or the faces go up, or sometimes maybe we make all 3 go up. Okay. So that's what Euler realized, and so that's why we have Euler's characteristic of connected edges, connected graphs. Now we're going to look at unconnected graphs. So as I said, connected graphs, you can go from any point to any point on without having to get off of the lines. Okay, I can reach this point from this point by following the graph along. Any point on the graph I can reach from any other without getting off the graph. Versus here we have an unconnected graph. There. So here's an unconnected graph with 2 parts to it. So if I wanted to get from this point to this point on my unconnected graph, I couldn't stay on the lines. I couldn't stay on the edges. I could not traverse the edges, so to speak. I'd have to stop off, get off. Okay. So here I have the outside counting as a face for both of these. So the outside is a face for both of these, and then I have this one face as well. For vertices, I have 1, 2, 3, 4, 5, 6 vertices. For edges, I have 1, 2, 3, 4, 5 edges. Get 3. What I'd like you to do is see if you can discover a pattern for unconnected graphs. So try a few more unconnected graphs where there's just 2 pieces and see, are you always getting 3 or is there something else at work? Once you've figured out what's going on with unconnected graphs that have 2 separate pieces, then check out unconnected graphs with 3 pieces and 4 pieces. See if there's any pattern that goes on. And if there is a pattern, see if you can figure out why. Okay, with the single connected graph, we were able to see why. See if you can figure out why with 2 or 3 or 4 pieces. I'll come around and see how you're doing, see if you need help at all. You can work with the people around you if you like. Just go ahead and draw 2 pieces, or if you want to go right to 3 pieces. And yeah. Don't make them too complicated unless you want to keep counting them. Two. Now you, oh, these are 2 again. Okay, good.
So the outside, we have two statements.
That's two.
So what if I don't ring the letter?
There are lines that fall between the vertices. This one is one. You can do a mess of one. Yeah, you can be as complicated as you want.
Okay.
Yeah. Here.
Okay.
Yeah.
Yeah.
For this, there's one more thing for the outside of focus.
What is this? The one?
Oh, that's what I got. Okay, so you have three, and now you're gonna do this. Oh, then you got seven. So you're seeing the
Yeah, because
pattern.
it's just well, I'm working the GB.
Okay. So these two you did?
Did you go watch it?
Three faces.
Yeah, bro. It's gonna be. It's gonna be.
So you have three faces to the outside, it's one face to the inside. So is that a three?
My brother.
Yeah. Okay. And the vertices one?
Dude, I was originally gonna go sing. And I saw that it was private and shit. And I was like, what? Hey, it's a good. I'm pretty sure it's a good school. So it's guys. Like, I've never heard.
Oh. There's eight of them.
Yeah, no, it's very expensive.
Oh.
Have you given me some drawings done and counted? What are you getting?
Oh, that was a nice and simple way to do that. Very nice. And then you've got a pattern there. Is anybody stuck? Raise your hand if you're stuck. Well, I saw a lot of you getting to 2, so we'll go ahead and talk about the 2 together. If you have 2 pieces to your connected graph, what does it always come out to? 3. Yeah, always comes out to 3. And then, if we have 3 pieces, we can emulate one of the students I saw who did just the simplest connected graphs. So you have one face that they all share on the outside. One, 2, 3, 4, 5, 6 vertices and 3 edges. 4. Okay. Anybody else get 4 when they did 3 pieces? Yeah. Okay. Go ahead. See, lots of hands went up. Okay. Great. So, did anybody do 4 pieces? I think I did see someone do 4 pieces. What did you get for vertices minus edges plus faces? 5. Good. Yeah. So there is a pattern, isn't there? When you add, yeah, it goes up 1. Does anybody see why it's going up 1? So we already have Euler's characteristic of a connected graph with a single piece, one connected graph. And that's 2. But when we put another connected graph in there so that there's two separate connected graphs making up your unconnected graph, we don't add 2 on by adding another because of that shared face. So because of the shared face, when we add another piece on, we only add 1 more, not 2 more. So that's how that pattern is working out. Well, one of the things that the Euler's characteristic of connected graphs is used for is for proving the Platonic solids that there are only 5 platonic solids. So when you made the platonic solids, you made all there are. So we're going to move to 3 dimensions. So I'm going to do a connected graph on a balloon in 3 dimensions. I always have a horror of this. I'm pretty sure I'm terrified it's going to pop. I think my brother used to chase me around with one and pop it on my head. I really do. That's some kind of a phobia. I don't know the name for it. All right, so here's a connected graph on a balloon. So when I put a connected graph on a balloon, I still have v minus e plus f is 1, because I have the outside face, and then each of these loops is a face, so that's 3 faces. On this drawing for edges, I have, the edges are the enclosed by the 2 vertices, so I have 1, 2, 3, 4, 5 edges. For vertices, I have 1, 2, 3, 4. Those are the beginning and ending are your vertices and where the lines cross. So that drawing being on a balloon doesn't change anything. I still have Euler's characteristic of connected graphs. Well, we can do a 3D drawing of our cube or any of the platonic solids on a balloon. So I'll put the cube on the balloon because that's actually the easiest to draw on the balloon here. Okay, so there's one face, and then I'll draw the bottom face. Okay, and then I'll connect my sides, the top and bottom connect. So this is called a stereographic drawing of the platonic solid. It's projecting the platonic solid onto the balloon shape. But it still has the features of the platonic solid. It has the essential features. It has the same vertices, same number of vertices, edges, and faces. They're just drawn on the balloon shape instead of being made out of straighter edges. So if I put the cube on the balloon, it's the same as a squiggly drawing on a balloon. This is a drawing from your author. If you take the air hole on the balloon right here, and you take this face that the air hole was on, you can stretch it out. And that's why the outside counts as a face, by the way, okay? So we take this air hole and we stretch it out, and this outside now becomes that face that had the air hole on it. And here's the 4 sides that connected to the bottom. So when we say v minus e plus f, we're still working with a connected graph. These all make a connected graph. So our vertices on the balloon, there were 8 corners, there were 12 edges, and there were 6 faces. And that still brings us to 2. So your textbook in this section looks at the proof that there's 5 platonic solids by carefully counting. You should never underestimate the power of just counting. So by counting the possible edges on all the different ways you can make regular polygons into shapes, we come up with the proof at the end of your section 6.2 on how many platonic solids there are. So you can look at that proof if you want to, but there's only 5 platonic solids, and hopefully you've made them all. If you have any questions, see me after class. I'll see you on Wednesday.